Lesson 2.3, density curves and a normal distribution.
So we're looking at density curves and the normal distribution. Selena works at a bookstore in Denver International Airport. She takes the airport train from the main terminal to get to work each day. The airport just opened a new walkway and that would allow Selena to get from the main terminal to the bookstore in 4 minutes. She wonders if it'd be faster to walk or take the train. So the dot plot shows the amount of time it has taken Selena to get to the bookstore by train each of the last 1,000 days. So we want to know what percent of the time did it take Selena 4 minutes or less, because that would be faster than the train, right? So when is she, going to be faster? There's got to be a better way than counting all of these dots, right?
Why is it so wobbly as well?
It's because it's plotting all of the decimals in between accurately. So this dot plot is accurately plotting 2.03, 2.01, 2.05, and that's why it's not perfectly lined up, okay? Because it's all possibilities from 2 to 5 minutes, okay? Any decimal that's possible in between. She recorded how long it took her to get to work. So another approach to this model, to model the dot plot, is with a density curve. If we look at the graph, it's pretty uniform, right? I mean, it has a few little peaks in here, but this is a pretty uniform graph. It seems like it's distributed evenly the different times it might take her to get to work. So instead of counting all the dots, we can approximate with a density curve. When we start from 2 minutes to 5 minutes. So that's how many minutes? 3 minutes, right? A density curve, the area must add to 1. Okay, so let's write that down as the first thing we write down in our notes. In a density curve, the area must add to 1. Or the area must be 1. So if we have 3 minutes on the x-axis, in this rectangle, the height of the rectangle has to be 1/3, so that 3 times 1/3 equals 1. Okay, that's what determines the height of the uniform density curve. And it's not much of a curve, it's a straight line, right? But we're going to look at curves a little bit more later. So we can find an approximate proportion using the curve, not the exact. The exact, we would have to count all those dots, but we can get an approximation. So again, we talked about why the height is 1/3, because the area has to add to 1. So if this is 3 minutes, 3 minutes times 1/3 would give us 1, which is 100%. Here's some other things we need to know about a density curve. So this we want to write down. A density curve models the distribution of a quantitative variable with the curve that is always on or above the horizontal axis, has an area of exactly 1 underneath. The area of the curve and above any interval of values on that horizontal axis estimates the proportion, right? It's always an estimate of all observations that fall in that interval. We were interested in finding out what percent of the time it takes her less than 4 minutes to get to work using the train, because it would take her 4 minutes to walk, right? So that's why you see the graph divided by this blue and red areas. So we want to know, what's that percentage? Well, how many minutes is along the x-axis? 2, right? And 2 times 1/3. 2 times the height, 1/3. 2/3, which is 66.67% of the time. So 2/3 of the time, she gets to work in less than 4 minutes. And so that would be the answer to our question, right? That's more than half, so I think it's probably a better idea to take the train. She's going to get there faster 2/3 of the time than it would take her to walk. Suppose we use our calculator or a computer random number generator to produce a number between 0 and 4. Like 0.845552 or 0.3111119, the random number generator will spread its input uniformly across the entire interval from 0 to 4 as we allow it to generate a long sequence of random numbers, as we let it to just continue to generate numbers from 0 to 4 over and over again. Let's draw a density curve that's going to model this function. So you're going to write some of this down. This is an example we're going to do together. So you're going to write down, let's see, randomly produce numbers between 0 and 4, and then draw a density curve. Okay, write those things down. We're going to randomly produce a number between 0 and 4, and then we're going to draw a density curve to model this function. And then you're going to start by drawing this box. So if this box is going to represent our density curve, what's the lowest value on our x-axis here? 0. And what's the highest? 4. What does our height have to be to make the area 1? 1/4. Right? If our x-axis is from 0 to 4, which is 4 numbers, right? The height has to represent 4 times something that will give me an area of 1. Okay? So 4 times 1/4. If there was 5 numbers, we went 0 to 5, what would it be? It would be 1/5, right? 0 to 8, it would be 1/8. Okay? Then it says B, about what percent, so this will be writing down, about what percent of the randomly generated numbers will be between 0.87 and 2.55. So let's divide this up here. So that's 1, 2, and 3. 0.87 is about here. 2.55 is about here. We want to know what that area is going to be. Okay, so we should be adding that. You might want to make a separate drawing for B. That's up to you. Let me move it up a little bit. So can you find that area? Base times height, right? The area, is it 2 exactly? Can we find the exact difference of the base there of that rectangle, the red rectangle? How am I going to find that? 2.55 minus 0.87, right? That would be the length of our red rectangle. Yes? Okay. With your calculator, we get 1.68. So if the base of my rectangle is 1.68 and my height is 1/4, what is my area? Multiply, right? Times that by 1/4. And I got 0.42. So 42% of the numbers generated are between 0.87 and 2.55. Okay, now C is asking for the 65th percentile. I'm going to draw the model again, the distribution, the density curve. And I want to know what number represents, that's probably a little far, 65% of the data. That doesn't work, it does not show up. So what number here, n, represents 65%? How might I figure that out? Remember that this percentile means that 65% of the numbers are below this value. So what did I do here? I took the base, right? I took the base length times the height of 1/4, and that gave me the percent in part B, right? But that percent was in a decimal. How can I work backwards? Right, I have 1/4 times n equals 0.65. I can divide by 1/4, or what's our trick for dealing with the fractions? Multiply by the reciprocal. Algebra. N equals 4 times 0.65. 2.6 is the number that represents the 65th percentile. Wait. 65% of the random numbers generated are below 2.6. Okay, so I want you to draw these pictures, density curves and the normal distribution. Density curves come in many shapes. Some are skewed to the left and single peaked. Some are roughly symmetric and double peaked. We call those bimodal. And some are skewed to the right and single peaked. Okay. Remember that the title here, density curves and the normal distribution, is the title of the notes. It's just on every slide. So that you don't need to keep writing that over and over again, but you want to write density curves come in many shapes. One of our measures of center and variability apply to the density curves as well as the distributions of quantitative data. Recall the mean is the balance point of the distribution, right? So the mean is where your curve is balanced. It's not how many values, but it's the size of the values, right? So when it's skewed, the mean is moved a little bit more towards the tail. And those are our balance points. So this wouldn't balance enough. It's not in the middle enough. Back in the middle of the peak is not going to balance either because these numbers are bigger. So just kind of center, little right of that peak is where it might balance. So that's the idea you're thinking about when you're looking to estimate where the mean is you're looking at where that balance point might be. If it was on a scale, right, where would the center of that scale be? Or a seesaw, right, where would the center of that seesaw be? To make it balance. Now, the median is the halfway point where 50% of the data is on one side and 50% of the data is on the other. So that means the area is divided up. The median of the density curve is with half of the area on each side. So a skewed left distribution, again, the median is not at the peak of a skewed distribution. It's slightly towards the tail. The mean is going to be more towards the tail, right, if it's skewed to the left, because these are going to weigh heavier. The outliers, the more extreme values, weigh heavier on the mean than they do the median. If it's symmetrical, your median is right down the middle. Okay, it will be right at that point of symmetry, on the axis of symmetry.
So if it's skewed to the left, your mean is going to be less?
Then the median, yes. And if it's skewed to the right, our mean is going to be greater than our median. Okay. If the data is skewed to the left, like this one, the mean is going to be less than the median. Opposite for skewed right. The mean is higher than the median. Whichever way the tail goes, that is where your mean is going towards. The median stays right smack where 50% of the area is below it and 50% of the area is above it. So here is definitions, official definitions of mean and median of a density curve. You may have written this down from the other sides. It's just summarizing it, putting it together. The mean of a density curve is the point at which the density curve would balance if it was made of solid material. And the median is the equal areas point, the point that divides the area under the curve in half. So definitely write this into your notes. Okay, so a symmetric density curve balances at its midpoint because the two sides are identical, so the mean and the median of a symmetrical density curve are equal, right? This is not different from when we talked about symmetrical dot plots, symmetrical histograms, stem and leaf displays. If it was symmetrical, the mean and the median are the same. Well, for a density curve, a lot of it's theoretical, right? We're just estimating, so they're exactly the same in a symmetrical density curve. It's not so easy to balance, to spot equal area points on a skewed density curve, but the mean is greater if it's skewed to the right, right? We just said that. And the mean is less if it's skewed to the left. So here is a picture of a density curve. It models, we don't know what variable it models, but we have three lines, A, B, and C. Which one do you think is the mean? And which one do you think is the median, A, B, or C? So take a second. You're going to, with the person next to you, which one is the mean and which one is the median? Should our mean be smaller or larger than our median? It's going to be smaller, right? The mean is going to be smaller than our median because this is skewed to the left. The mean moves to the left. Now, does the peak of our density curve divide if it's not symmetrical? No, that means C should not be the mean or the median. The only time the peak is our mean or median is when it is symmetrical. So which one is going to be the mean, A or B? A, right? Skewed to the left, A is going to be the mean because it's smaller, and that makes B the median. Okay. Because the peak of the distribution, if it's skewed, is not the balance point. It's not the halfway point. So the halfway point, if it's skewed to the left, is going to move to the left. The halfway point, if it's skewed to the right, is going to be to the right. And so we were correct. I didn't want you to write that down. That's why I didn't put it in there. What is this? a strange look. Okay, so now we have a histogram of the scores of all 7th grade students in Gary, Indiana on a vocabulary part of the Iowa Basic Skills Test. Why are they taking an Iowa test in Indiana? I don't know. The scores are grade level equivalent, so a score of 6.3 indicates a student's performance is typical for a 3rd month of grade 6. The histogram here is roughly symmetric. Both its tails fall off smoothly from a single center peak. There are no large gaps or obvious outliers. So we can draw a density curve over the histogram to describe the overall pattern. That density curve is called a normal curve. So we can approximate the scores of these with a normal, it's approximately normally distributed, which is going to mean symmetric and unimodal. The distributions described by normal curves are called normal distributions. There are several important facts about normal distributions as illustrated by the 2 density curves below. All normal distributions have the same overall shape. Symmetric, single-peaked, bell-shaped. Okay, so what I want you to write is normal distributions, and then I want you to write down these attributes of shape, center, and spread. The mean, mu, is located at the midpoint of the symmetric density curve and is the same as the median. And the variability, the standard deviation sigma, measures the variability of a normal distribution. You can estimate standard deviation by eye on a normal density curve. Imagine you're skiing down a mountain that has the shape of a normal distribution. At first, you descend at an increasingly steep angle as you go out from the peak. Fortunately, before you find yourself going straight down, the slope begins to flatten rather than steeper. So that point where it flattens, like it's going steep and then it kind of changes to not as steep, that is how far the standard deviation is. No. So that's just to kind of help you learn to estimate standard deviation by looking at the data. It's like that point where it goes from steep and then all of a sudden it's not as steep. And good, well-drawn graphs will show you that. When we draw them by hand, it's hard to do. Okay. The normal distribution is described by a symmetric, single-peaked, bell-shaped density curve called the normal curve. Any normal distribution is completely specified by only 2 numbers, the mean and the standard deviation. A density curve being normal is the description of the shape. It's a specific shape. Single-peaked, symmetric, so symmetric and unimodal, has a mean of mu and a standard deviation of sigma. For normal distributions, it's often denoted with a capital N, and then with parentheses, the mu and then the sigma inside. But those would be numbers. So if you saw N 24,6, that means the model is normal with a mean of 24 and a standard deviation of 6. Let me repeat myself. In baseball, a player's batting average is the proportion of times that the player gets a hit out of the total number of times at bat. The distribution of batting averages in a recent season for Major League Baseball's players with at least 100 plate appearances can be modeled by a normal distribution with a mean of 0.261 and a standard deviation of 0.034. We're going to sketch the curve and we're going to label the mean and the points that are 1, 2, and 3 standard deviations from each side of the mean. So what should you be writing down? All you need to write down is that we're talking about batting averages and the mean and the standard deviation. The rest of it is just background information that you don't need in your notes. Okay? So write down batting averages, Mean mu equals 0.261 and standard deviation 0.034. Now we can abbreviate this by saying n 0.261, comma 0.034, because it says it's modeled by a normal distribution right here. So how are we going to draw it? So we're going to make our best attempt at drawing a normal distribution. What? Nope. There's no way to turn them into whole numbers. We just got to use the decimals. But we have a calculator. Decimals aren't so bad with a calculator. All right, you guys ready? Yes, ma'am. In the very middle of our distribution is our mean. 0.261. Mean goes in the middle. If you're not following along on this part, you're going to want to skip what you're copying down and follow along on this part. Okay? So we're going to estimate about 1 standard deviation. There's that kind of mark, right? Where it's changing from steep to not so steep. And we're going to make 3 marks along our axis on both sides of the mean. And I want to know, this is mu, this is 1 standard deviation above, 2 standard deviations above, and 3 standard deviations above the mean. And this is 1 standard deviation below, 2 standard deviations below, and 3 standard deviations below. So I'm going to add the mean, I'm going to add the standard deviation to the mean, and write that number down. I'm going to do that 3 times. Then I'm going to subtract the standard deviation from the mean and do that 3 times. Okay? With my calculator. So 0.261 plus, what's my standard deviation? 0.034 is 0.295. I always add first. Then add 0.295, 0.034 again, 0.329. I'm just adding 0.034, adding 0.034, and adding 0.034. 0.363. Now subtract it to get the numbers on the other side. Go ahead and do that. When you're asked to draw the normal model, label the mean and the points, I don't need to write the plus 0.034, right? I just wrote that to show you what I was doing. So when I subtract 1 standard deviation, what do I get? What did you get for the first one? 0.227. Then we're going to minus 0.034 again. 0.193, and then subtract 0.034 again. 0.159.